Today is the last topic for this course. It is Algorithmic State Machine or ASM. The state machine designed based on a state diagram that you already learned. In practical, it's not so flexible to indicate characteristics of complex state machine, and it's hard to modify state machine if some detail change, and is quite unclear for algorithm expression to show how the process depending on inputs. Since algorithms involve action sequencing and data manipulation, so the state machine design can be considered as two parts. The first one is control unit. The second one is data part. The control unit is for control, start, and stop action in data unit, raising condition and designing what to do next according to circumstances. For example, generating control signal to load data to enable and disable register. Data path or data unit. Data path or data unit is for store, route, combine, and process data. Okay. The state machine design methodology is similar to programming. Actually, there are ASMs and hardware description languages, such as HDL or Verilog. Anyway, for this course, we will study just only ASM. Okay, AMs, okay, design. Normally start from draw ASM chart. ASM chart is similar to flowchart in programming, but the difference is ASM chart, okay, work repeatedly, not stop. For the more flowchart in programming, maybe start, right? Start and do something, okay? And sometimes we have some condition. Okay? If yes, do this one. If no, maybe do another one. Okay? And when finished, so we go to end and stop the process. But ASM is work repeatedly, not stop. And ASM chart, okay, each state of state machine will complete the process within 1 clock. Okay, the detail we will see later. Okay, to design, you should know the component of ASM chart. Okay. The first one is step box. One step box. This one is decision box. And sometimes we have conditional output box. Okay, for state box. State box, it must be in every state to show state name and it binary code. For example, state idle, and 00 is state code for idle. Inside this box, number is show the output if this output based on the state. Namely, if this output is more type, output like multiple state machine and register operation. For example, clear or load. But please remember that for register operation, actually it's just to assign the value for control signal. Something like, for example, register or counter. Sometimes it has enable, right? Enable signal. For example, if I want to clear register R, clear this R, so maybe the register have clear input, right? If I assign 1 and here to clear the register. For the design, normally clear or load is synchronous, clock synchronous control. Namely, it must wait for clock tick to operate load or clear action. So this one just apply the control signal, okay, to activate or make clear or load or enable signal become active. But the real action will not do until clock tick. Okay? It must wait for clock tick. That means if clock is not tick, the value in register R still be not non-zero. Okay, still be not unclear until clock tick or change to another state. So the register is cleared. Okay, when clock tick. Okay, be careful. Okay. And decision box. Decision box, you may write in this one or this style. For example, if x is input, sometimes we check x is 0 or not, right? This is condition box. But sometimes if it's quite long condition, for example, x is 0 and y is 0. Okay, if you write this style of condition box, okay, quite offer large space. So to save the space, then we cut this area. So it's become this shape. So you can use this or this shape, okay, to express input condition. This condition is input variable. For example, x is input. If x is 1, go to this, and if y is 1, go to this. Or you can write if y is 1 and x is 1, go to state B. Note that to check x is 1 or y is 1 in the circuit, it's combinational circuit, right? So the circuit must complete the operation, okay, before clock tick. That means the final result must be complete before clock tick. So you can do x input comparison that is 1 or not, or check Y later, or check Y first, then check X later, or check them at the same time. It will be the same result, right? Same result. Okay, so it's not important, right? To compare X first or Y first. And conditional outputs box. Or for this one, for example, this one is input variable, okay, in decision box, right? And if this input start is 1, some output will be active or some register will be assigned to, for instance, PC. PC will be from program counter. This register, okay, will be clear. So this one will be clear when start is 1. If input start is 0, it's not clear. That means this one is like merely type, right? Merely type output, because the output not based on only state, but based on input also. Okay, so for example, this one is in the same state. In this case, is the state name is idle. This state eval is output based on state only. Namely, if idle, if it's in state idle, this output will be active. Okay. So this eval will be 1. State idle, eval is 1, right? And when clock tick, if start is 0, so it's go to state idle. Should be state idle after clock tick. Okay, this is still be idle state. And if start is 1, for example, change to 1, right? When change to 1, we go to this direction. So for this one, register A will be clear. But not clear suddenly. Okay, just assign clear signal to this register. But the clear operation will do when clock tick. That means when start is 1 at here, the register A to be not change the value, right? It's what wait for clock tick. When clock tick, it check Q0 is 1 or not. Now Q0 is 1, so let's go to this state. When clock tick, okay, A register A is clear, and change to state mount 1. Okay, this state write nothing. That means no any output active. So output eval then become not active. Okay, to save the space, right? We will write normally we will write just only active output, because the system maybe have many output, right? If we write all output that become 1 or 0, okay, it take large space to write. So we will write just only active one. Okay. Now let make familiar with ASM chart. For example, this one, state even, state odd. This one is odd parity checker. Odd parity checker. Do you remember? For this system, maybe something like this. Input X and output Z. For parity, for example, to check that number of logic 1 that come to the input X is odd or not. If yes, output is 1. If no, output is 0. For example, at the beginning, and so input for the first clock tick is 0. So now number of logic 1 is 0, right? So output Z is 0. For the next clock tick, if input is 1, so now total number of logic 1 input is 1, is odd. So now output output Z is 1. And for the next clock tick, if input is 1, now total number of logic 1 is 2 or even. So now output then become 0. It's not odd. Something like this. So this state machine then have two states, even or odd. Because there are two states, so we can use only one bit, right? State variable, maybe Q, right? If Q is 0, it shows that it's state even. If Q is 1, the state is odd. For state even, output Z is 0. Z is 0. You can write nothing. And at state odd, output Z is 1, right? It's active. So you write just only active output. But some people, if someone can write this one is okay, right? Z is 0 is okay. But for the system have many bit output or many outputs, okay? If you write all output that is 1 or 0 is not comfortable. So normally we write only active output. Okay, now if the state is at state even, when clock tick X is 0, it still be state even, right? But when clock tick X is 1, we change to state odd. And if input X is 0, it still be at state odd. But if X is 1, when clock tick, go to state even. Okay. So if X is 0, okay, state not change, but X is 1, change to the another state. And from this one, you can write something like state output or transition output table. Namely, this present state or current state. If okay, I write in this state output table from this ASM chart. Okay, there are two states, even and odd. Even and odd. And one input X. X can be 0 or 1, right? 0 or 1. Okay. If input X is 0, state not change. If present state or current state is even, the next state still be even. If present state is odd, next state is odd. But if input x is 1, okay, you change event to odd and odd to even, okay, for the next step when clock tick. And output will be active or become 1. Okay, for active high output, okay, will be active when the machine is on state odd. And from this, okay, you can assign, okay, do state assignment, right? To assign binary code for state. In this case, assign 0 for state even and 1 for state odd. So then you replace, right, state name by its binary code. First of all, event change to 0, odd change to 1, and output if it's active high, so write 1 for active output and 0 for not active output. And from this you can decide, right? You can decide to define, for example, circuit F, and in this case you use only one flip-flop, right? Maybe you will use D flip-flop, okay, and output logic G. And because output Z is the same value of state variable, so for circuit G, there's nothing, right? Just wire, okay, to connect. Output Z directly to Q. For circuit F, input from external input X and feedback from output flip-flop Q, and the output of F is D. You can decide by this one. Namely, if you use D flip-flop, when clock tick, you do read data from excitation signal D, right, or output F. So the value of D is the same as Q star, right? So you can use this table as excitation table, okay, table to show the value of excitation signal. So you can use this one to design circuit F, right? Namely, in this case, there are two variables. So you can use this one to write K-map or two table. Namely, in this case, D is 1 when X is 1 and Q is 0. So D equal X and Q prime, or when X is 0, Q is 1, or X is 0, Q is 1. Or you can change to XOR, right? Q. Okay, this is circuit F. Okay. Next, for this one, just show you how to convert state diagram to ASM chart, or convert back from ASM chart to state diagram. Okay, for this one, it show more types, right? State machine. Namely, sorry, this one is mirror type state machine. right? Because output, okay, is based on state and input. Also, X is input, Z is output. System, something like this. Input X and output Z. At state A, at state A, at state A, when input X is 0, X is 0, output Z is 0. When X is 1, output Z is 0. X is 1, output Z is 0. And what about state A? The next state of A when clock tick go to A, right? So when X is 0, go to state A. But when X is 1, go to state B. X is 1, right? Go to state B. Okay. For state B, when X is 0, output is 1. At state B, when X is 0, output Z is 1. But when X is 1, output is 0. X is 1, output is 0. Okay, this is mirror type output. Okay, the output value is based on the value of input. For example, this one, when X is 0, output is 1. If input change to 1, output change to 0. And at state B, when clock tick, if X is 0, go to state A. When X is 0, change to state A. But if X is 1, go to state C. Go to state C. At state C, if input X is 0, output is 0. If X is 1, output is 1. X is 0, output is 0. X is 1, output is 1. For state A, when input is 0, change to B. Input X is 0, change to state B. When X is 1, change to state A. And for this one is mode type, right? State machine output based on state only. So you can write output inside this state box. Okay, for example, at state A, output is 0. At state B, output Z is 1. At state C, output Z is 0. Okay. Or you can write it as very active. Okay, if you blank this one, that means output Z is not active. So that means Z is 0 at here and 0 at here. And maybe you can write just for Z. That means it's active. Okay. Okay, and how about stitching? At state A, when X is 1, go to B. When X is 1, right, go to B. When X is 0, go to A. At state B, when X is 0, go to C. When X is 1, go to A. X is 0, go to C. At state B, when X is 1, go to A. At state C, when X is 0, go to B. When X is 1, go to A. When X is 0, go to B. When X is 1, go to A. Okay? And because there are 3 states, right? So it needs at least 2 bits, okay, to represent, okay, the state. In this case, I use 00 for state A, 01 for state B, and 11 for state C. Next example. Example 3. is for 8-bit side to complement calculator to define to complement. Do you remember? For example, if the binary value is something like this, if I want to find 2 complement of this one, the 2 complement of this one, when you add together, the result must be 0, 0, 0, 0, 0, 0, 0, 0, right? For all bit. Okay. So if this one is 0, so this 0 right here, 0, 0 right here, 0, 0 right here, right? This is 1, so it must be 1 here. Then we add 1 and 1, it becomes 0 with 1 carry out, right? And this carry out will be carried in for the next digit. So when you add 1, add something, and add carry in this bit, so this must be 0, right? 1 and 0 and 1 is 0. And again, this carry out. This carry out become carry in for the next digit. Now 0 add something, add 1 is 0. So this must be 1, right? 0 add 1 as carry in 1 become 0 with 1 carry out. Again, this carry out become carry in for the next digit. 0 add what? Add 1, right? And then add carry in 1, then it's become 0. Okay, 1 is here. Again, carry in is 1. So it must be 0 right here, right? So you know that to find 2 complement of any value, you calculate from LSB. If it's 0, okay, the result of 2 complements to be 0. Be 0, 0, 0, right? And for the first digit 1, it's still be 1. But after that, it's the opposite, right? 1 to 0, 0 to 1. Okay, 0 to 1, 1 to 0. Because after this, the addition for every bit you have carry in. Okay, based on this algorithm, so at the beginning, at the A, if input x is 0, output z is 0, it be 0. If x is 1 for the first x, output z is 1. But after that, so it's changed to state B. At state B, if x is 0, output is 1. If input x is 1, output is 0. Okay, that's all. Okay, and the next example. This one is single parser. Okay, this circuit, okay, the output Z will be 1 for 1 clock period when input X is 1. And then the output Z will be 0 until the input X becomes 0 and then change to 1 again. Okay, what does it mean? Okay, let's see. We still have 1 input and 1 output. When clock tick, input X is 0, nothing change, output still be 0. Okay, when clock tick, X is 0, output is 0. But when clock tick and can detect that X is 1, okay, when X is 1, so now output Z become 1 for 1 period of clock. Okay. That means when clock tick is back to 0. Okay, and it must wait that x must be 0 and back to 1. Okay, that means when clock tick at here, if x to be 1, not change, right? It must wait. It must check that x is 0 or not, right? If x is 0, so it wait for the next x is 1. Okay, then it's become 1 for 1 period of clock again. This situation is something like this. Wait the user, right? When the user pressed the input switch, then it's generated. Okay, 1 clock pulse. If the user still be pressed, okay, so they still be pressing the switch. Okay, the output still be 0. It wait the user released, okay, or remove the finger from the switch, and then when the user press switch again, so the next power will be generated. Okay, from this problem, so we can write ASM chart like this. At start, state start, no any output active. So that means output Z is 0, okay, for this state. And if X is 0, it still be state start. When X is 1, go to state pause. This state output Z become 1. And when clock tick, go to the next state. State wait, this state output become 0. When clock tick, okay, change to state wait, output becomes 0. This state, okay, it wait input become 0, right? If input X still be 1, so it still be at state wait. So output check is 1 still be state wait. But when X is 0, when X is 0, it go to state start. And then to check X is 1, right? If not, if X is 0, still be state start. And when X is 1, okay, go to state pause again. Okay. When you obtain this ASM chart, so you can design, right, the state machine. Okay, like this example. And for complicated state machine, obtain some register inside. Okay, you need to design data unit also. For example 5, okay, I just show you the diagram of ASM chart. As they start, at the start, we assign initial value of register A, M, Q, and counter. And then check the value Q 0. Okay, it is 1 bit of multiplicand is 0 or not. If yes, okay, achieve the value of register A and counter. If not, it as A with M, need to update value, and then check the value C0 is 1 or not. If yes, halt, stop the process. If no, then it's repeat, right? Okay. Okay. The detail that we will let you do as homework. Okay, something. And this one is show that if you get this M chart, okay, you can determine, okay, the register or device that need for implement data path or data unit. Okay, for the detail of this, okay, process, okay, I will explain by the next example. That is this one. Example 6. This is binary divider. Actually, there are many algorithms, okay, to do division. For this one, I will use this algorithm. Namely, for example, there are 1, 2 input x, y, and start. Start is just control that this circuit will be operate or not. And ready just show status of the circuit that ready to operate or not. If it's during the process or not finished the calculation, so ready will be not active or become 0. But if free, right? Namely, if it's not on process or finished the process, then it's ready to do the next calculation. So ready will be 1. Okay, and for the result of calculation, you have put Q at the answer and R is remainder. For example, if input X is 20, Y maybe 3. Okay. So this algorithm we will compare X is greater or equal Y or not. If yes, then we will subtract Y from X, namely 20 minus 3, then it's 17, right? And then count up Q. And then because the result X update, right? Now X is 17. It's still be greater than Y. Y is 3. So minus 3. Then it become 14. And minus 3. Minus 3. 8. Minus 3. It's become what? 5. Minus 3 become 2. Now it's become 2. So this condition is not true. So it's false. So it's go to out of this while loop. Okay, so 2 is remainder, right? And the result of this divider circuit is 1, 2, 3, 4, 5, 6, right? It's 6, right? With remainder 2. Okay. So from this algorithm, okay, you can write M chart like this. As state idle, ready is 1. Namely, it's ready to proceed. Just wait for start input. Okay. If start is 0, okay, do nothing. But if start is 1, okay, go to state initial. To assign initial value to register M, N, and Q with X, Y, and reset or clear the value of Q. After that, go to state wait. Before, compare the value M and N. That M is greater or equal N or not. State wait is important because at initial state, For example, register M variable in practical register maybe have load signal and input X. Okay, input X to register M register. At this initial state, just assign the signal to load to make it active. But the value of register still be not X. It's wait for clock tick, right? For clock tick. So if you have if there is no state wait, you cannot compare M and N, okay, correctly, because the value of M and N still be not X, still be not Y, right? It must wait for clock tick, okay? When clock tick load active, then read data from input and update to X. Okay, for register N also, for Q also. And if M is greater, I call N to state process and do subtraction and increase variable Q, okay, by 1. And then go to state wait, okay, and repeat this one until this condition become false. Go to state finish. Okay, at this state, ready become active, and assign the value of M to R to keep the remainder. And then when clock tick, go to state idle again, okay, to do the next calculation. Okay, from this every time there are how many states? 1, 2, 3, 4, 5. 5 states. That means you need at least 3 bits, right, to represent these 5 states. Anyway, if you can reduce state, that means you can reduce number of flip-flop, right? So, for example, at this step, initial, actually, you can merge or combine this action in state initial to assign initial value to register to idle state. I mean, at state idle, if start is 0, okay, you just wait for the user, right, to press the input to make start is 1. During waiting, you can do assign, right, initial value to the registers, right? If start is still be so, then you assign the same value. Okay, so that means you can reduce number of steps. Now it's become 1, 2, 3, 4. So you can use 2 bits to represent these 4 steps. Anyway, some problem occur if you use this. The result Q. The result Q is Q. Okay. When you finish the calculation, go to this one. When clock tick, is go to state idle, right? Okay. Now, if clock tick again, what happened? The value, the result in Q, then is clear, right? By this operation. That mean the result of division now is clear also. That means the result in Q you cannot use it, right? Okay. Or you can use just only one or two period of clock. This is not okay. So to keep this result, so you need to add more one more variable, okay, to keep the result. So now you can clear Q, and this W still be keep, okay, the result of division. Okay, if you use this one, so now you can determine the device for data path or data unit. For example, based on the behavior of M used to what? To keep the value of x, y, and for the state updates with this update with this subtraction M minus N. So you can use register as M. For N also is register, right? To keep the data of Y. But for Q, how about Q? Q, this state is 0, right? This state is one increment. So you can use counter for Q. Use counter for Q. And what about what else? For this one is comparator and subtractor and register R, right? To keep M and register W, okay, to keep the value of Q. Else, oh, this one, this state you assign X to M, right? This state you assign M minus N to M. It's different. So you need multiplexer. Multiplexer. Okay. Maybe it's X for this state and M minus N for this state. Okay, to assign input to register M. So when you know all device that you need to implement data path, after that you just draw the diagram. For example, register N, okay, get input from Y, right? Register N. That means when clock tick at this state idle, the control load signal N must be 1 to load data from Y. Okay, but state wait, state process, state finish. Okay, you maybe apply 0 here to make this register is not active. Namely, it keep the value. Okay, keep the value in hold mode, not read the data from its input. And register M. Register M at this state idle. If you load data from X, Y, that means load must be active. Load M is enable control, right? Load M must be active at this state. And multiplexer must select input from X, namely select signal must be 0 at this state. Okay, so when clock tick, you will raise data from X, but at state process signal must be 1, right? It is subtracted m minus n. You feed to register m. And at this step process also, okay, the control signal load m must be 1. When clock tick, then is the read, okay, data from m minus n. And for register R and W is similar one, right? Register R, okay, receive data from M. So output from register M connect to input of register R. And W, right, from Q. Q is counter. Okay, that's all. So this is data part. So now you must assign the circuit, okay, to apply control signal. Apply control signal to each register, right? Okay, and maybe generate, okay, output signal of the step machine, something like ready. Okay, now okay, let's go to the control unit design. To design this control unit, actually you can start from this ASM chart. Okay, it's very easy. Okay, from this M chart, okay, you can use it to design control unit. Okay, by copy the M chart, okay, but change the detail inside in the state box, namely this one ready, output ready. Okay, it's still the same. For this one, this operation will be operate when load M active, right? When load M active, okay, to get data from X. So load M active and select must be 0. Okay, this state select is 0, but because it's not active, so so it's not right in this state box. But for this one, select is 1. Okay, select is 1. Okay, it's 1. So write it. But in practical, if you want to make here clear, you can write select at here. Also, that select is 0. Okay, it's okay. Okay, but for the example, to save the space, so I write just only active signal. Okay, for n, okay, get data at this state. So load n must be active at here. Okay, for Q is 0 is clear, right? Clear signal of counter will be active at this state. Okay, state wait nothing. State process. Read data from m minus n. So this one select must be 1, right? Select active, and load m must be active also. Q plus 1 or count up, right? Count up must be active. Enable input of counter, and this state finished. Okay, plus load data from m and q, right? That means load R must be active. Load W for register W that read data from Q must be active. Okay, that's all. So now you obtain the M chart for control unit already. And from this one, okay, you can write down something like state output table or transition list. Okay, For example, I write down with a transition list. Namely, it shows a current or present state. There are 4 states, right? So I use 2 bits, right, to represent each state. In this case, I use 00 for state idle, 01 to represent state wait, 10 for state process, 11 for state finish. So I write the current state. And at state idle or 00, if input start is 0, just go to state idle, right? So start is 0, still be at state idle. Okay. Next state, Q1 start, Q0 start is 00. But if start is 1, you change idle to wait. That means change 0 to 01. 00, if start is 1, go to 01. And at state wait, this one. At state wait, if m is greater or equal n is 2, go to state process 10. 1, go to 10. If not, go to 11. 0, go to 11. At state process 10. When clock tick, go to state wait 01. Okay, no input condition. That means it's always 1. Okay, and 11. Okay, it's the wait for clock tick to go back to state idle. 11 to idle. Idle is 00. Okay, no input condition. That means it's always 1. Okay. And from this, you can design what? You can design the state machine for controlling it. Namely, there are 2 flip-flop, right? Maybe you use D flip-flop for Q1 and Q0. And your work is to design circuit G and F. Okay. And for convenience, this example, I will use decoder to design this combinational circuit G and multiplexer to design combinational circuit F. Okay, you already know, right? You know that any combinational circuit can design by using decoder and multiplexer. Okay, so this one. Okay, for Q1, Q0. Okay, let's design circuit G first. For circuit G, the output of control unit is what? Is this one, right? This is output, right? This one is output from control unit. So the decoder will generate output based on its input AB, right? If input AB is 00, Y0 will be active, right? Okay, if it's 01, okay, Y1 active is 10, Y2 active is input is 11, okay, Y3 active. So ready for ready for ready output be active at state 00 or 11, right? So when it's state 00, while 0 active. When the skip at state 1 1, right? So it's make AB become 1 1, while 3 active. So you just OR, right? While 0 or while 3, okay? To generate output ready signal. And for load M, at here and at here, state 0 or 1 0. 0 1 0 active, right? It's 1 0 y 2 active. So y0 or y2. Okay, generate control signal load M. For load N, just already state 0. So y0 is load N. Clear Q also already state. So you can use this y0 signal as load N and clear Q. And what else? Up is already state, right? So you can use y2 and up to control counter to count out and select this one at this state. What else? Load R, load W. Load R, load W is 1 1. When the machine is at state 1 1, its make input of decoder is 1 1, so Y3 active. So you can use Y3 as load R and load W. Okay, that's all for output logic E. How about next state logic F? Sorry, next state logic F. This one. Okay, I used multiplexer. Okay, let's consider this transition list. So if I use D flip-flop, right? If I use D flip-flop, let's consider Q1 star first. If I want Q1 star to be 0, that means I must apply 0 at here, right? Okay, now let's consider Q1 first. Here. Now, D1, I connect to the output of multiplexer that controlled by Q1, Q0. Okay, Q1, Q0 from present or current state. If Q1, Q0 is 0, 0, Q1 star is 0, right? So I apply 0 at here, 0, 0. But if present state Q1, Q0 is 0, 1, you read data from 0, 1 channel, right? 0, 1 input. So now Q1 star here is 1. So apply 1 at here. And for state 1, 0, Q1 star is 0. So you apply 0 at here. And for state 1, 1, okay, want to be 0. So you apply 0 at here. At this address 1, 1. And state and how about the value of Q0 star at state 0, 0 is become 0 for start is 1 and it's become 1 when start is 1. So it's same as value of start, right? So you apply start into this 0, 0 address. At state 0, 1, here Q0 start is 0, 1. It's opposite to the result of this comparator. Okay, it's 1, 0, but this one is 0, 1. So you inverse, okay, the result from comparator. And this state is constant 1, so apply 1 at here, 1, 0. And at state 1, 1, Q0 start is 0. So you apply 0 right here. That's all. Okay, for next step, logic F. Okay, now it's finished the design. Namely, now you obtain this control unit to generate signal, okay, to control the device in this data unit. Okay, this data unit or data path. Okay, this signal from control unit. Okay, the detail of this control unit. Okay, is this one. Okay, that's all for the lecture.